Voltage division in AC circuits is an extension of the classic resistive voltage divider concept, incorporating the frequency-dependent behavior of reactive components. In AC, alternating current, capacitors and inductors offer reactance, which is denoted by X_C for capacitors and X_L for inductors, and that affects how the input voltage is distributed across the circuit elements. Unlike purely resistive circuits, the voltage division in AC depends on the magnitude and phase of each component's impedance, making it essential to consider both the amplitude and phase angle when analyzing signal behavior. Reactance is the frequency-dependent opposition to current flow presented by capacitors and inductors. It's a component of impedance, which is the total opposition that a circuit element offers to alternating current. Impedance is denoted by Z, is a complex quantity that combines resistance, R, and reactance, X, in the following way, and here's a formula. Z equals R plus Jx. Here, J is the imaginary unit, and reactance X can be positive for inductive reactance or negative for capacitive reactance. In a purely resistive circuit where X equals 0, the impedance is real. In a circuit with reactive components, though, the impedance is complex, and both the magnitude and phase of the voltage and current are affected. The magnitude of the impedance is given by this formula. Absolute Z equals to the square root of R squared plus X squared. The relationship is important in voltage division for AC circuits, where voltage is divided not just by resistances, but by the magnitudes of impedances. For example, in an RC voltage divider, the output voltage depends on the relative magnitudes of R and XC, both of which determine how the input voltage is split. Now, understanding the role of reactance as a component of impedance helps explain how capacitors and inductors influence circuit behavior at different frequencies, and why voltage division formulas in AC analysis use Z instead of just R. The reactance of capacitors and inductors changes significantly depending on the frequency of the input signal. The reactance of a capacitor is given by this formula. Xc equals to 1 divided by 2 times pi times F times C. At very low frequencies, based on this formula, when F approaches 0, Xc becomes very large, and this means that a capacitor behaves like an open circuit to DC and low frequency signals. On the other hand, at very high frequencies where F approaches infinity, Xc approaches 0, and the capacitor behaves like a short circuit that allows high frequency signals to pass through easily. Let's have a look at the reactance of an inductor now. So the reactance of an inductor is given by XL equals to 2 times pi times F times L. At very low frequencies, when F approaches 0, XL becomes very small. An inductor then behaves like a short circuit to DC and low frequency signals. On the other hand, at very high frequencies, when F approaches infinity, XL becomes very large, and the inductor acts as an open circuit, blocking higher frequency signals. These frequency-dependent behaviors are fundamental in the design of filters, where components are chosen to either pass or block specific ranges of frequencies. And understanding how Xc and XL change with frequency is essential to predicting and controlling circuit behavior in the frequency domain. Let's consider a simple AC voltage divider composed of a resistor and a capacitor in series. The output voltage is taken across the capacitor, and this is the schematic for this particular example. Here we'll examine the AC voltage divider of this circuit. Now in this circuit, the resistor has a constant impedance, while the capacitor has an impedance that is given by this formula, ZC equals to 1 divided by J times omega times C. where omega is the angular frequency. The voltage division across the capacitor changes with frequency due to its reactive nature. As you can probably imagine, when the angular frequency becomes very large, the impedance of the capacitor becomes very small, until eventually, for practical purposes, it becomes very close to zero. The voltage divider rule in AC circuits is similar to the resistive case, but it uses complex impedances instead of real impedances. For the above circuit, the output voltage across the capacitor is given by this formula. V out equals V in times ZC divided by R plus ZC. When we substitute the capacitor's impedance, we have this formula where V out equals to V in times, and then there's a division here. On the top side, we've got 1 divided by J times omega times C, and the bottom, we've got R plus 1 divided by J omega C. This expression can be simplified to analyze both the magnitude and phase of the output voltage. The magnitude of the voltage division ratio is given by this formula. Now this formula shows that at low frequencies with a small omega, angular frequency, the capacitor's impedance is high and most of the input voltage appears across it. As the frequency increases, the capacitor's impedance decreases, reducing the output voltage magnitude. A similar approach applies to RL circuits, where the inductor's impedance is ZL equals J times omega times L, leading to a voltage division ratio when the output is taken across the resistor or the inductor. I've also prepared a Python script to demonstrate these concepts in an RC circuit. So this particular script demonstrates the voltage division in an RC circuit by plotting the reactance of a capacitor and a resistor over a range of frequencies. The script compares the reactance behavior of the resistor, which depends on the frequency, against the resistor. In this plot, you'll see how reactance behaves differently for a resistor and a capacitor as the frequency of the signal increases. The flat dashed line shows the reactance of a resistor. It stays constant at 100 ohms no matter what the frequency is. And this means that a resistor always offers the same amount of opposition to current. It doesn't care if the signal is slow or fast. It resists the same way across all frequencies. The curved line shows the reactance of a capacitor. At low frequencies, this line is high, which means the capacitor resists the current strongly. But as the frequency increases, the line drops, showing that the capacitor offers less opposition to the current. In other words, the faster the signal, the more easily it passes through the capacitor. The key lesson here is that a resistor's reactance doesn't change with frequency, but a capacitor's does. And this helps explain why capacitors are used to filter out certain frequencies in electronic circuits. Now let's consider an AC voltage divider composed of a resistor and an inductor in series. This time the output voltage is taken across the inductor. And here's the schematic for this example. We'll examine how this voltage divider behaves in the presence of inductive reactance. In this circuit, the resistor, again, provides a constant impedance. The inductor, however, introduces a frequency-dependent impedance that is given by this formula, ZL equals J times omega times L. This impedance grows as the angular frequency omega increases. In other words, inductors resist changes in current more strongly at higher frequencies. When the frequency is very low or close to zero, the inductor behaves almost like a short circuit, offering minimal opposition to current. But at very high frequencies, the inductive reactance becomes large, impeding the current flow significantly. We use the same voltage divider rule as before, this time applying it to the inductor. And the output voltage across the inductor is given by this formula that you see right now, where V out equals to V in times ZL divided by R plus ZL. Substituting the impedance of the inductor, we get this formula. V out equals V in times J omega L divided by R plus J omega L. And from this, we can determine the magnitude of the voltage division ratio given by this formula. This equation tells us that at low frequencies, when the value of omega is small, the inductor's impedance is small. So the voltage drop across it is also small. But as the frequency increases, the inductive impedance increases as well, and the output voltage rises accordingly. This frequency-dependent behavior makes inductors, just like capacitors, useful in applications where we want to allow high-frequency signals to pass while blocking lower frequencies, such as in certain types of filter circuits. Here I've got a Python script that plots the reactance of both the resistor and the inductor across a wide frequency range. This will help you visualize how the inductor's reactance changes with frequency and how it compares to the resistor's constant impedance. In the plot, you can see that the flat dashed line again represents the resistor's constant impedance of 100 ohms, unaffected by frequency. The curved line represents the inductor's reactance. At low frequencies, it's close to zero, meaning the inductor does not resist the current much. As the frequency increases, the inductor's reactance rises sharply, showing that it opposes higher frequency currents more strongly. The key insight here is that while a resistor always resists current equally, an inductor resists changes in current depending on how fast those changes are. And this makes inductors, as I mentioned earlier, valuable tools for managing frequency-dependent behavior in AC circuits. So out of all this, what should you remember? Here's a list. In AC circuits, the division of voltage across components depends on both resistance and reactance, the latter being frequency dependent. Reactive components introduce a phase angle, so voltage division must consider both magnitude and phase. The output voltage across a reactive component in a series is given by this formula, where Z reactive varies with frequency. Understanding voltage division using reactance is fundamental for designing filters and other AC circuits where signal control is essential.